Everyone, welcome to APEC. It's January 16th, and I'm your moderator, Tim Ventura. First, I would like to thank everyone for joining us today on this call, and I want to do a big shout out to everyone watching us on YouTube live stream as well. I'd also like to thank Mark Sokol and the Falcon Space team, and give a giant thank you to today's scheduled presenters, Ron Evans and Nick Pope. Ronald will be presenting on the BAE Greenglow project, and we also have Rob Chambers here. We're going to try and squeeze him in if we have time. He has some stuff to present as well. And Nick Pope is going to be joining us in about 2 hours to talk about UAPs. After that, Mark will be showcasing some progress on his latest projects, and again, showing us around his lab. I have a couple of quick announcements, and this is mostly for our YouTube viewers. If you can, please take a moment to sign up for our email announcement list. Right now, I have a copy of that up at americanantigravity.com/events. Again, that's americanantigravity.com/events. Now, since I'm speaking of websites, Jeremy Reese has also been updating alienscientist.com. And again, he live streams this on his channel. He's got over 100,000 subscribers. So take a moment and visit him at alienscientist.com. And we are also in the process of building a brand new dedicated APEC conference website, which should be finished in the next week or so. So again, thank you to everyone for joining us, and let's welcome Ron Evans to the call.
Am I set to go?
You're all set, sir.
Okay, away we go. I've got my scarf on because some people recognize me with the scarf. And I wear the hat because I am bald. I'll show you all, but it keeps me warm and I like to have that on. Right, so Greenglow. First of all, I'm going to read from my notes. So thanks to Tim for inviting me, and wishing everybody a happy new year. I expect Tim has already done that. So this is going to be about Project Greenglow, which is anti-gravity or gravity. And I've got some further ideas which we'll hear about towards the end. I joined British Aerospace in 1978, a long time ago now. When I arrived, I was an expert in fluid mechanics. So, and I had been working at university on an investigation looking at wings with vortices coming off them, because it was quite clear that the next aeroplane was going to have foreplanes. Makes the aeroplane lighter, but then you've got the vortex from the main wing interacting with the foreplane wing. So I'd been working on that. I applied to work at BAE, that's Walton. That's, if you know the geography of England, it's North England, near a seaside town called Blackpool. I was hoping to work with the fluid mechanics, computational fluid mechanics group, because they'd been working on the same things. But I didn't end up there. I ended up working for the group which was involved with performance and propulsion. And I, in fact, ended up in the drag section. So it was quite, well, I hadn't been expecting that. Most of the time, where are the slides, Tim? So have I got a slide up here so that I can see them?
Oh, sure. Would you like me to put them up, or do you want to put them up?
I'll leave you to do it.
Oh, okay, absolutely. So let me do that then. I have those right here. Okay, I am just waiting for it to load. Okay, and please let me know, everybody, if you can see me okay. Can you see the slideshow?
We can see it. Just make it full screen.
Yeah, it is. It is.
Okay, so we've seen that one. We can move on to the next one. Now you can see my scarf. So I'll just say next for next. Okay, right. So we're now into the analogies of physics. I'm a mathematician. Mathematicians love patterns. It's not that we're lazy, because once we've got something, we can just change the symbols and it means something else. So on the left-hand side here, we have the fluid mechanics model. So the blue circle is a source. You can imagine a kitchen tap and the water pouring out. That's a sort of one-dimensional source. When it hits the floor of the sink, it spreads out in 2 dimensions. And the blue lines are the streamlines, and you can put dye or milk or something in to actually see them. And we can have a sink, which is just all the water going back in this time. We can have a vortex, and you've all seen the vortex. Well, these days everybody has showers, I suppose, but if you have a bath, you see the vortex going down the plug hole. If you grab hold of that green vortex with your fingers going round in the direction that the water goes round in, your thumb will point in the direction of the vortex. And that's called the curl of velocity. And we can have a smoke ring. Sorry, I'm just reading a message from Gary. Right, so that a smoke ring. And there, if you look carefully, you can see that the fluid going in one side and coming out the other. So it's like having a source and a sink. They will give you the same flow pattern. The middle one is electromagnetism, when we can have a positive charge where the electric field lines go outwards, and we have and also a negative charge. And again, we can have a current flow, and we get, this time, we get a magnetic field around the line. So that, what's happening? Okay, so that is very similar to the vortex. And at the bottom, we can have what looks like a smoke ring, but this time it's a solenoid, and we can have a virtual source and a sink. Now, the next one is gravity. In fact, gravity was the very first one that we had, but we only had it for static situations. And we only know about mass, which is an acceleration sink. Whether we can have an acceleration source or negative matter, nobody knows. Everybody thinks, well, a lot of people think it's not possible. Some people think it might, and there have been other ways of making such a thing. Now, if you move mass going along with the other analogues, why don't we get a graviton-magnetic field? Perhaps we should do. No one's ever seen it, not in a laboratory on Earth. And if we have a spinning mass, then that's going to look like a smoke ring or a solenoid. So why didn't anybody ever see the graviton-magnetic field? And why hasn't it been made use of? The reason it's not been made use of is because somebody called Gottfried Leibniz, who another man who created calculus at the same time as Newton, introduced something called vis visa. It turned out that vis visa, which was just m times v squared, but if you took a half of it, it turned out to be the kinetic energy. We didn't need the graviton-magnetic field, so it wasn't detectable as far as anybody knew, but we could do without it anyway, so why bother? Newton didn't understand energy. Well, he certainly didn't make use of it, and he wasn't bothered about vis visa. But Newton's mechanics developed with kinetic energy. Well, let's go on a bit further, but just to say, if you change the velocity, you'll get an acceleration. If you change it here, you get an acceleration, and that acceleration of a magnetic field gives you an electric field. If you knew about the graviton-magnetic field and you could change it, you would create a gravity field. Well, that's what we want to learn about. But working with kinetic energy doesn't tell us anything about it at all.
Now, Ron, would you like me to go on to the next slide, or are we still on this one?
Next slide, please.
Absolutely, sir.
So as I was saying, when I came from university, I'd hoped to work with the fluid mechanics group, but I ended up in the drag section, probably because the boss of the performance group was actually another Leeds graduate. And since I was a Leeds graduate, he probably thought, oh, right, I know this sort of person, I'll take him. And I ended up in the wind tunnel. It was interesting. It was all data analysis. You're a mathematician, you do it. Next slide, please. In 1979, a photograph was sent to the publicity department to somebody called David Camille, who was head of publicity, and he didn't know what it was. Very strange looking craft. He asked the aerodynamics people. Actually, I didn't see it, but they sent it to the chief aerodynamicist, and he showed the deputy chief and other people. Nobody knew what it was. The next year, the chief aerodynamicist had to go down to RAE Farnborough, just south of London. It's where all the research was done right from the First World War on aerodynamics. And at the meeting, which was given by somebody from the United States, they were told all about the 117 and all its strange shape. So we now knew what it was. It had actually been flying over the North York Moors. Nobody knew what it was. It was a UFO, a real UFO. Well, the chief aerodynamicist came back and thought, right, we need to make sure we've covered this. I was one of the last people in the department. I was a mathematician. I'd studied electro-magnetism. Oh, right, we'll use him. Go and find out about stealth program and set something up for us and make sure everybody in the aerodynamics office is well aware of what's going on. So I was given the job. And the first thing I did is I looked for the reports, and to my surprise, in a way, I realized that the United Kingdom back in the 50s, even the late 40s, was an expert on stealth. All our bombers at that time had stealth features put on them, mostly RAM. The RCS paper on the now was secretive, now unclassified, but it described all the work that had been done back in the 50s. And I actually met the man who was responsible for the program. You can see his name on that report. It's Grant Dawson. The next thing that I did, I've lost the pictures, but never mind. The next thing I did, I went to Thorn EMI. Is this important? I've got something to do with you, Tim.
Yeah, sorry about that. I'm fighting with my computer real quick. Okay, you know what? Here, let me quit and reopen it. Okay.
Okay.
I'm going to take it out of slideshow mode. And guys, please don't annotate or draw on the screen if possible, because that's what. Okay, here, let me do this. Okay, can you see that okay?
Yes, thank you.
Okay, and let me go back down here.
That's the one I want.
Okay, perfect.
So the middle slide is the scale model radar range down near Bristol. And so I went there and wow, they had lots of scale models and it was well used by the United States. I met several Americans there at the time. So they were well into stealth by then, but of course they'd already got the F-117. I don't remember seeing an F-117 model there. I may have done. I certainly don't remember. Anyway, the mathematician I met down there was Dudley Bird, and the man that was responsible for a lot of the work was called Sid Woolcock. I don't know whether any of you had any work on the stealth side, a name you'll maybe recognize. The next thing I did is I went to the Plessy company down at Towcester, which is sort of down in the south west of England. And they make radar absorbing material. And I met somebody there called Bernard Wickenton, who had actually been to Germany at the end of the war to see how the Germans made RAM, because they'd been using RAM to line up the leading edges of their night fighters, because they knew darn well that's how the British fighters were catching them. And also They've been using RAM on their submarines because they knew they'd been caught on the surface with their snorkels and conning towers. They were all covered in RAM. Okay, so next slide, please. Next slide, please. Next slide, Tim.
Yeah, sorry about that. I'm having some issues with, but let me put it back up. Okay.
I'm glad it's you and not me.
Oh, no, it is me. Let me apologize to you. I believe this is our next one, right?
Okay, right.
Okay.
I got a phone call in 1983 to say, you're going to be moved to the Advanced Technology Group. I said, no, I don't think so. I'm running the stealth program. So I went to see the chief aerodynamicist and said, I don't want to go. He said, well, you've got to. You're a mathematician. He said, I've got plenty of managers, but we haven't got very many mathematicians. So you'll have to go. So I did. And the man in charge was called Tom Smith. In the 50s, he'd been working on what was called Mustard, which was a multi-unit space plane. And there's a model of it in the Smithsonian Museum in Washington. Later on, in the 1960s, he headed the HOTOL program. You may have heard of them, I don't know. But there we are. There was the radar, millimeter radar system. The idea was that they were going to fly this and pick up the signature of tanks and be able to actually identify them. British Aerospace wasn't the only company working on this. There was another company called Marconi in the UK and several companies in the United States. And they all got together and compared data. Well, they tried to, they couldn't. There was something wrong. All the data that they'd collected on tanks all seemed to be different. So my job was to go through the data analysis that we'd collected and try to put it into some form that could, and then collect other people's data and match it. So that's what I did. I spent some time doing it, but eventually I came up with a method and we could then investigate everybody's data and check it all out. So that's what I did. After I'd finished doing that, I had to work on several other things, which I can't mention really. But anyway, I went to the boss and said, you know, we've worked all this, spent all this money on stealth. Maybe somebody clever is looking at using the gravitational signature of something. I mean, you can see a ship, a battleship, using it with gravity at 3 miles. Okay, an aeroplane's a bit more difficult, but as we'll see towards the end, the MOD have come up with some ways to look at signatures, and McDonnell Douglas back in 1991 were also trying that system. So we knew it was possible. So I said to the boss, you know, can we, well, can I go and check this out? I said, yes, if you think it's worth it, you do that. Next slide, please. So the first thing I did is I went to talk to a professor at Imperial College in London, who back in 1974 had given a presentation at the Royal Institution in London. The Royal Institution was made famous in the 19th century by several people, but the first two was Sir Humphrey Davy, and the person who really made it famous was Michael Faraday. So the Christmas lecture by Eric Laithwaite was all about gyroscopes, amongst one thing. Professor Laithwaite thought that gyroscopes could be explained by something that we now call the GEM equations. If you look at the slide, you may recognize Maxwell's equations at the top there. And there's those curl terms that we looked at right at the beginning, and you now know what a curl is. It's just you grab hold of whatever it is, and twist your fingers around in the direction of either the magnetic field, the fluid lines, or the gravitomagnetic field. So there we are. Let's look at the GEM equations. And the first one says curl of gravity equals the change of the gravitomagnetic field. That's the H. The next one to it, which is that upside down delta with a dot G, is in fact Newton's formula. That's Newton's only bit. So in Newton's gravity theory, that's the only bit. All the rest isn't used. That's because we don't use gravitomagnetism. We use vis-vis or kinetic energy. Now, what we want to find out is, can we find out what gravitomagnetism is? Can we jiggle it? Because if we can, we might be able to create gravity. Now there's equivalencies. You'll all be familiar in terms of gravity is equivalent to acceleration. If you're in the lift and it accelerates upwards, you feel heavier. So that's an acceleration. Gravity is a field. You can make an effect across space and have an effect on a mass. You can't do that with acceleration. You actually have to push on the mass to make it accelerate. So though they're equivalent, they're not the same, because one's got field properties, the other one hasn't. Now we come on to H, or gravitomagnetism. That is equivalent to angular velocity. If you've got a gyro and you spin it, it's got angular velocity. But to make that spin, you have to actually spin the mass. But gravitomagnetism has a field property. Why can't we see it? It's so incredibly weak because, let's go back to magnetism. Magnetism, if you look at the first equation, curl E, it's got a mu sign there. That's the permeability of the magnetic field across space. Now come on to the analog down at the bottom, curl of little h, and you can see there's a gamma. And if you look afterwards, there's what's called B equals that peculiar sign, which I call eta. B equals eta h, which is at the bottom on the right-hand side. Now, if you're looking on the right-hand side of the picture, the speed of light squared, I'm sure you all know, is 1 over epsilon mu. That's the permittivity of electric field in space times the permeability of the magnetic field. And underneath there we've got c squared. Again, the speed of light squared. That's 1 over gamma, which is, I prefer gamma, it's a better feel for me, but gamma is equal to 1 over 4 pi big G. That big G is Newton's inverse square effect. But notice that if we look at c squared, I've got 1 over gamma times this, what I call eta. Now that eta is the permeability of the H field in space. Turns out to be absolutely tiny. Next slide, please. We had a chance to, what I didn't mention to you was Professor Lathwaite got in trouble because he demonstrated an inertial thrust machine. And there were a number of academics in the audience that didn't believe it. One of the inertial thrust machines that was around at that time was called Kidd's inertial thrust machine. He was a Scotsman who lived up near Dundee. Kidd wasn't the only one. There were a number of other ones. Some of them had actually been patented. So Kidd was quite willing for us to test his device at Wharton. It was on the news, it'd been on television. So we tested it. There's a picture of it at the bottom left-hand corner there. It was two gyros which waved around, up, waved and span, and they joggled up and down. And in throwing themselves up and throwing themselves down, they created enormous accelerations. But did they actually change weight while they were doing it? We put it on a bungee because the bungee would just damp out the accelerations. We weren't interested in the size of the accelerations. We were interested, was there any change of weight? And we did the tests, and the top one there, you can see that within the error band, we couldn't see anything at all. On one occasion, they seemed to be outside the error band, seemed to say, oh, bit strange. We weren't sure. So that was one out of, I forget how many, 20, I think, that we did. It was July 1991. There was no way, as we will see later, we could carry on doing any more. So we weren't very good scientists. If you have an anomaly, a good scientist will keep poking it to find out what caused it. So unfortunately, we weren't able to do that. Next slide, please. Now, 1989, I think, 1989, I had an opportunity to go and visit Dr. Robert Forward. Now, if you know anything about gravity studies, Robert Forward has been one of the people that's been pushing it, he's a pioneer. And, so I went up right to the north of Scotland. You may have heard of the nuclear power station there, Dounreay. Well, he lived in a cottage at Ray, which was actually just near Dounreay. He wrote a paper in, oh, I should say, he got his PhD working with Joseph Weber, working on that, looking for gravity waves. Joseph Weber had come up with a long metal cylinder, rather like an antenna for detecting radio waves. They also came up with another device which they called a gravity interferometer, which was actually built where Robert Forward was employed, which was at the Hughes Research Laboratory at Malibu. That's another story. So Robert Forward had written this paper saying, theoretically, it should be possible to create anti-gravity with, I put the picture at the bottom there, with a toroid. And with the toroid, if it's electric, it will create a magnetic field inside. If you change the electric field through the toroid, then that blue magnetic field will change. A changing magnetic field creates a gravity field. And that gravity field I've shown, an electric field, a changing magnetic field creates an electric field, which I've shown by that straight line, black line there in the center. And he gave us a model, which when you check it out, it's an approximation, but it's perfectly theoretical. But there are some theory, you have to make assumptions. And at the top there is the electric field that you create. And I've put E epsilon mu, that's the free space value of the permeability of magnetism. And mu r is the relative permeability. And that's the changing current. And there you are, A squared is the radius of the electric lines there in the toroid, and R is the radius of the whole toroid. Okay, I'm just reading that. I'm not sure what that's about. Now, Robert Forward talked about changing those electric toroid and having a big piping and passing fluid through it. But he said it was impossible. However, if you think about it, electric charge has got both charge, but it's also got a gravitational charge as well, because an electron has an electric field and it has a gravitational field. So you could, I put it in, so that's not in his paper, but it's perfectly feasible to write it like that, where again you've got eta naught. Now that eta naught is 10 to the minus 20, sorry, yes it is, 10 to the minus 26. This is why Forward said it won't work. But notice the relative permeability. Now that, probably small, but we don't know what it is. If we go to the one above it, the mu r is the relative permeability of magnetism. Generally, that's between 0 and 1. For a superconductor, it's 0. For most materials, it's about 1. But for some materials, like a material called mu metal, is 50,000. 50,000 is a bit different to 1. Now, we don't know about eta R. There may be materials which have properties of 50,000. That suddenly starts to make a difference. They might be more than that. They might be 50 million. I don't know. Until someone is able to look at a gravitomagnetic field and start poking it about, we won't know. So in my mind, I have wondered, you know, Robert Forward, did he go back to the Hughes research place and say to somebody, oh, I wonder whether it's possible to change that eta R and make something work. And then we would have a gravity field created too. Next slide, please. My boss, Tom Smith, retired in 1990. As we'll see later, a lot of people were retiring. In 1977, the aerospace companies were nationalised, but were denationalised in 1977. So in 1978, when I joined, it had only been denationalised 1 year. All the time, the company was changing, trying to get itself sorted out. In 1990, Tom Smith had been working for what was first English Electric, then British Aircraft Corporation, finally British Aerospace. And in 1990, after 40 odd years, he retired. So I got a new boss who decided to call it something new. He called it Business Strategy Department, or British, no, it wasn't. It was called the Future Business Strategy Group. By that time, I'd been working for Tom, and Tom Smith had allowed me to investigate this gravity side. And I'd organised a meeting with several universities within the UK. And we'd come up with a meeting in March 1990. And there's the list of things that we studied. So gravitational wave research was very popular. I mean, would it ever be possible to use gravitational waves to detect aeroplanes? I mean, that's a bit like the work that Gary Stevenson was working on with his high frequency gravity waves. Fifth, fourth experiments at that time in 1990 were in the news. The superconducting gravity gradiometer is a way of moving submarines, for instance, without having to make any noise with your sonometers or anything like that. I was more interested in Faraday's gravity experiments. Very few people seem to have followed it up. There was the quantum effects in microgravity, which has gone on in the past 20 or 30 years. I was again interested myself in Heaviside's linearized gravity theory and the gem equations. These gem equations were first studied by Maxwell himself. He wondered, having developed the electromagnetic model, well, why it looks very similar to gravity. And he'd pondered over it for a while, and then he busy starting other. He had to start the Clarendon laboratory in Cambridge. He was far too busy to bother with it too much. Heaviside was a mathematician in the 1890s. He had a look at it, but decided that parameter, that field, the eta, the permeability, was too small. So he didn't pursue it either. We had somebody coming up from Kent who looked at a new model of the electron, and we had somebody from Birmingham University looking at gravitational things. So it was all ongoing. It was very interesting. I published a report. Next slide, please. And that report was sent off to the library, and the library put it on the exchange with NASA. NASA had an exchange agreement with British Aerospace, and they would swap documents. So that went off to NASA. I don't know what we got back in return. Well, in fact, I do. We got back a report called an electric propulsion study, which actually looked at more than I'd done. I hope you all know about the electric propulsion study. It's on the floor down there. If you haven't asked me in questions and answers, and I'll tell you about it. Now, what I hadn't realized is that the technical director, who was a nuclear physicist originally, he was quite interested in my report, and he wanted it because he was going to be made a professor at Salford University. Salford is where the British aerospace apprentices went. Just check my time. What am I up to? I need to get a bit of a move on. So he asked me to tell him about it. I showed him it. He read the report. He sent me off to Salford to talk to the people there. I explained it to them and they said, oh, yeah, that's all legitimate. I went back and told him. He said, good, I'll go and give it. I didn't want to be made a fool. And there he asked the people in the future concepts thing, draw me some pictures, draw me a GA, and I'll take those with me. Off he went. It went down so well. He came back. He was so pleased with himself. He gave the lecture at the Institute of Mechanical Engineering in London. That got publicized, went to the press. Then he had an interview on the radio. Next thing he knew, we had all sorts of people asking him for more information. And that's where Nick Cook came in, because Brian Young, who was the technical director, said to Nick Cook, you go and talk to Ron Evans. I think he'd had his fun and he didn't want to be involved with any more. So Nick came and talked to me, or rather I went to talk to Nick. And later on, the Hunt for Zero point appeared where Nick mentioned the BAE program, but he was more interested in what the Germans had been doing during the wartime, and also what the United States had been doing. Would anybody tell him, were they working on stealth? By and large, they wouldn't. He came back thinking, well, maybe they are, maybe they're not. Next slide, please. So I'll go to this very quickly. As I said to you, we were still restructuring. 1990 was a very difficult time. So that BAE was selling off things left, right, and centre. They were still the biggest exporter for the United Kingdom. They were having talks with DASA about merging. Early on in the year, they thought they might have been bought by GEC, but they managed to get through that. And then in 1999, they managed to buy Marconi from GEC. And then in 1999, that became BAE Systems. So there were a lot of changes going on where I was working, and they closed some of the sites, and there are other sites. In fact, if Rob Chambers is there, perhaps he will tell us whether they closed Plymouth at that time. I can't remember when they did. So 1990, I was in the Wharton Advanced Technologies side. I'd got a small group doing various things. Everything was very part-time. Lots of studies going on. I had to remember a four-legged robot walking around the department at the time when all the problems going on. It wasn't looked on very favourably. Next thing I knew, the exploratory studies group had been closed, so I'd had to get another job. I'd only got another job for about a year, and then that was closed and I had to look for another job. I thought I was going to be made redundant. Fortunately, the person who had taken over the stealth group that I'd started said, well, come and work with me. So I went to work for him. That was lucky. Then in 1995, there were so many people wanting to be managers that the technologist career branch was started. So I ended up being an advisor. Mathematicians aren't seen as specialists. They're sort of generalists. So next slide, please. Right, I think we can just go through this very quickly, but this is really the start of Project Greenglow, because with the technologists, they'd actually got a little bit of money. In 1980, again with all the company in flux really, Wharton had a lot of research money at the time. In fact, when I'd responded to the interview in 1977 to apply for the job, they were the biggest research and development aerodrome in Europe, and they had a lot of research money. But in 1980, the headquarters in London decided, no, we've got what was the Missile Research Centre in Bristol. We're going to make that the BA Research Centre. So we want the research money from Wharton, we'll send it to Bristol. And if Wharton want to do research, they'll have to go through Bristol and get it done down there. So they'd lost a lot of money, but the technologists have got a little bit of money back. So in March 97, I'd got John Allen, who had been made redundant or had actually taken early retirement from Kingston. Kingston was where the Harrier and the Hawk were built, but they'd closed that site and that all that work had been moved to Wharton. But he came up to talk to us about the future of aerospace, and he talked to the future concepts engineers. And John, back in 1970, had written a book, and in it there was a chapter about gravity. He was very keen on gravity. His boss, whose name escapes me for the moment, wasn't too keen on John talking about gravity. Like so many bosses, it sounds like anti-gravity, and they're all scared stiff of anti-gravity. So that went very well. I asked John to do a study for us, and that's this blue report on the right there. Supposing we had an anti-gravity engine, how would it change aerodynamics, vehicles? So he went away and did that for us. That later became an AIAA paper. Also at the same time, I went to our local university, University of Central Lancashire, got a professor there to do a study. Faraday had been very interested in heat experiments, so I got him to do a study. It actually turned out to be something that had already been discovered back in 1897 by somebody called Leduc, but I didn't know that at the time. Then I went to a meeting with Robin Tucker at the University of Lancashire. Professor Robin Tucker was a professor of gravitational physics. So if anybody should know about anti-gravity, he should. He was a bit wary, but tackling it from an Einstein's general relativity side, he thought it was worth having a go at doing something. They had a team there of 4 or 5 general relativity people. So he suggested, why don't we come up with a joint program? We'll fund part of it, or we'll get money to fund it, and you'll have to fund the other. So I went back to the technologists, I proposed a program, and it was agreed very quickly, and we got something started. Robin Tucker became the academic advisor. So quite clearly, British Aerospace was not doing the research work. The research work was being done at United Kingdom universities. So Robin was the academic advisor. John Allen was going to be the design consultant. Now that might be done by BAE. So in 1997, that began the start. It was all funded. We had some small support from Rolls-Royce. We started with a lecture series. We had a couple of academics from Greece, Athens, I think. My goodness, we had a big audience from MOD, from Rolls-Royce, from BAE, and MOD, and those academics were given a hard time. Then in 1999, MOD contacted me and said, look, you should really be having a look at a photon drive. It's work that was done by the Soviet Union, and one of the people that worked on it was Sergei Vinogradov, then at Kharkov University, part of the Soviet Union. It's going to work with Paul Smith. So we got some funding from that. And then along came Podkletnov. It was all in the news. And then I learned that students at Sheffield University were also studying it. I don't know whether Clive is in your audience, Tim, but he will know. I went to Clive Woods and said to him, perhaps we could fund a little bit for you to check it out. And he agreed, a good idea. I've put a picture of Podkletnov's part of his device. The brown is his superconducting ring. It was the YBCO ring, yttrium barium copper oxide. It's called a type 2 ring, which becomes superconducting, getting near to room temperatures. And then those 3 solenoids are the thing that make it work. Now you're going to have to cast your mind back to that toroid. That, in fact, is a part toroid, isn't it? If I filled in the spaces, it would be a toroid. And what did Robert Forward tell us? That if you change the current, it created both an electric and a gravitational field. Now, Dr. Podkletnov had put his device in a metallic container and made it superconducting. It was metallic, it was a Faraday screen. No electric field could get out, but you can't screen against gravity. So maybe gravity did get out. Maybe yttrium barium copper oxide is this very thing we're looking for, the permeability of graviton-magnetism with a high value. I don't know. So on the right-hand bottom corner is one of Clive Wood's reports. Next slide, please. Right, we're halfway and I've only got a quarter of an hour to go. So John Allen did the study for us. I've mentioned that already. Done that, we've done that. Right. To Dundee. Right. Sorry, I'm just having to remind myself what I'm going to be talking about. So 1999 saw the formation, November 99, it wasn't really until 2000 that BAE Systems was formed. And everything came to a standstill in terms of research. All the money that we had at Wharton was frozen. So although the universities that were doing work, they carried on, we couldn't pay them any money. So the ATCs that were now, so that what had been the original British Aerospace Research Centre now joined with what had been the Marconi Research Centre. So the British Aerospace one at Bristol had dealt mostly with aerodynamics. They'd also, I mean, when I'd run the stealth program, I'd arranged to get stealth signatures, a program called G58. So we were starting to predict from modelling what the radar signature was. All that work went down to Bristol, and the team, I'm afraid, at Wharton had to go and find other work. But the people at Bristol, I better not say any more about this, I shouldn't really. So the team at the Baddow Research Centre, was at Great Baddow, which is in Essex, which is in southeast England. They were really working on electronics and systems and things like that. So between the two of them, they decided they shouldn't be funding Greenglow until they'd had their own look at it and had some assessment. So they had an assessment done by Glasgow University, and that's that blue report there. So that took a bit of time to do, and that had to be funded by the ATC, which included both of them, and it also included Rolls-Royce. They were interested to know what was going on, so that was funded. The report came back and they said that the Greenglow thing was really looking more at gravitational and gravitomagnetic fields. It was a field study. They thought it should really be more, or they ought to have more about the quantum aspects of gravity. And I think the reason was, about that time, Hal Puthoff and his colleagues had been looking at inertia and saying it could be a quantum effect. Anyway, the universities agreed to fund what Wharton had already started on, and we'd have to get some quantum work. So I managed to get people at Birmingham, Professor Clive Speake now, looking at Casimir study. They're actually using a superconducting gravity gradiometer, but they could do a Casimir study by the side with it. And the Lancaster University people, they went off to New Zealand to look at the gravitomagnetic field around the Earth. I'll say a bit more about that in a minute. And in 2000, we also got Mark Millis to come and give us a talk about what they were doing on the NASA breakthrough propulsion physics program, and then we told them what we were doing. In fact, at the time, well, I'll just tell you what happened. At the end of all of it, we were all getting on very well together, and Mark Millis arranged, I think it was probably through what was called EOARD, which is an American centre in London looking at all research going on in Europe. And the people at EOARD agreed to fund the university people that are working at Wharton to go and give their work, results of their work in the United States. Why United Kingdom can't fund things like that, I don't know. Sorry, I shouldn't be saying this. Not very good for UK. But UK will work on some things. The UK MOD supported what we were doing, but they were scared stiff it would be seen as a UFO study, and they couldn't afford to be mixed up with UFOs. Maybe Nick Pope might tell us something about that. In 2001, I got an introduction to somebody called Graham Ennis. I thought he was a UFO person, and he'd got what he called his Field Propulsion Conference at Sussex University. I was a bit apprehensive at the beginning. It turned out to be very good, and it turned out to have lots of what I call important people interested in field propulsion. People like Hal Puthoff were there. Alan Holt was there, and there were a lot of other people, if I could remember their names now, that you would recognise. But in 2004, that was the 3 years up, I thought we'd done a good program, but we hadn't made any breakthroughs. So it was very adventurous. It was a high payoff if we had made something, but it was very risky. Next slide, please. So in retirement, I thought we'd run a good program. So I sat down and I wrote a book. The first book I wrote was too long, but I trimmed it down, and then I tried to get an agent for it. Everybody, my children especially, tell me I can't sell books because I put equations in them. Okay, I went to 48 agents and publishers. They all said, no, thank you. One or two said, yeah, interesting, but no, thank you. So I persevered. Eventually, I thought, no, well, I'm going to self-publish. I want to leave a record of what we did, because I had the feeling that some thought that the people who had done it, and it had all been a part-time thing at Wharton, none of us had been allowed to work on it full-time. We all had other jobs. And I thought, without the record, it's just going to be forgotten. So I wrote it. And before I knew what, I'd got an email from the publishers saying they'd been contacted by the BBC. They wanted to do an Horizon program. Horizon is a science program. It's very well known. It's got another name in North America. Actually, I'd been contacted twice before by previous editors. I didn't dare say yes because I knew the managers at Wharton. I don't know whether they're jealous or just they didn't like things like that being aired on the TV. Again, probably it was the link with anti-gravity. So it was Steve Crabtree that contacted me. Was I interested? Well, I didn't work with BAE anymore, and I had some other ideas. I said yes. He introduced me to his producer, a guy called Nick Young, and a lady called, I'll remember her name in a minute. Sorry if she ever looks at this. It's very rude of me. Anyway, the voiceover was done by a man called Peter Capaldi. Now, you might not know him in North America, but he's Doctor Who in the UK, very well known. He's the 12th Doctor Who. So Nick Young got his program together. I was interviewed in various places. So he talked about the UK Greenglow program. He then went to visit Mark Millis and learn about that. He wanted me to repeat the Laithwaite gyro thing that had got Laithwaite into so much trouble at the RI. I wasn't so keen, but he said, you know, this is not just a science program, it's also an entertainment program. So we did it. He went off to Moscow to see Podkletnov and learn about that. He talked about anti-gravity propulsion. Some people said it can't be right. In my view, some of the academics that he visited made statements that, to my mind, are wrong. I remember one said it's impossible because you can't have a warp drive, because as a thing accelerates, it becomes, as the mass accelerates, it gets infinite in mass. But a propulsion system, a warp drive, has got a positive mass and a negative mass. And if you look at the mass equation, it's got a square root in it, Einstein's square root mass. Certainly the positive mass goes up till it approaches infinity when it's at the speed of light. But the negative mass is also negative infinity mass. And that approaches the speed of light, and the two cancel out. On the way, of course, they've both been accelerating and radiating off energy. So he went to visit the people at CERN who had been looking at antimatter, and they were dropping anti-hydrogen. I mean, I'm not an antimatter person. It seems to me at the moment, the view is that antimatter has got positive mass, but the people at CERN will tell us whether it has or it hasn't. He then went to interview Schauer, which is still in the news at the moment. Everybody said, no, that's not possible. So Mr. Dr. Schauer ignored them like all good engineers and said, oh, well, I'll try it anyway. And he seemed to get a tiny effect. I should say that our photon drive also had a very small effect. Our photon drive was open. Roger Schauer's is closed. Everything is inside. I've got some views about why it might work. Roger's got his own views. Other people have now tried it. I think Boeing have tried it, and I think other people have tried it too. There does seem to be something there. Nobody quite accepts the thing. In my view, engineers should try things like that, and then it's up to the mathematicians and other theorists to come up with the theory as to why it might work. Now, coming back to is it possible to use gravity to detect things? Well, the MOD have been working for a long time on a quantum accelerometer. At the moment, it can detect masses still in the meters, but you never know, in the future it might come up with something more. Now, the breakthrough propulsion physics, I forget when it was finished, 2002 or 2003, I think. Marcus Millis has started his own thing now. And Greenglow one ended in 2004. So there was nothing in the UK, nothing in North America. And in Germany, for EU, Dresden University, they started a program there. So that's still going. So Europe has now got a program. UK and North America hasn't, as far as I know. Right, now, what's the time? Am I all right just to continue on a bit longer, Tim?
Yeah, I would say keep going. It looks like you've only got a few slides left, so if you're able to just kind of push through them.
Next slide, please. Right, I put method of detection. So the first one, you'll know all about those. That's common ways of detecting magnetism. You might not recognize that long grey tube with a green laser beam through it. That's called Faraday rotation. I want to talk a bit more about that in a minute. Now, you can detect enforced rotation using a drive wheel. If you try to turn the flywheel around forcibly, you'll find it has its own deciding where it's going to go. And it's just vectors. So some vectors will tell you how it's going to move. There's something called a ring laser gyro, which was developed in the 60s and 70s. They're used in the aircraft industry for navigation, telling you where you are and things like that. And that will also detect rotation. But you have to fix the device to the device you want to detect whether it's rotating or not, like an aeroplane. There's also a much cheaper device called a fiber optic gyro, which are now fitted in all sorts of systems. That can also detect rotation, but again, you have to fix it to the device you want to twist. Now we come on to graviton-magnetism. which we haven't really detected yet. If you use a sphere, it has its own gravitomagnetic dipole. It has its own angular momentum, angular velocity as well. But if you put angular velocity into a gravitomagnetic field, it won't interact. But the gravitomagnetic dipole of that spinning sphere will, if it's strong enough. It has a gravitomagnetic dipole moment, and this is what they did in the NASA Gravity Probe B. So they had to have a field that was strong enough that that could be detected by a spinning sphere. I'll talk about that in a moment. And then again, you could also use a ring laser gyro. I'll talk about that in a moment. Next slide, please. Right, so this is NASA Gravity Probe B, nothing to do with Greenglow, but it's interesting to me. If you look at the underneath that black rectangle, it says HE equals 1/4 pi, blah, 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 blah. That is the analog of a dipole from electricity or magnetism. So that's where it comes from. It's exactly the same, and you can get it. It's a moment of inertia of the Earth, the angular velocity of the Earth. The distance from the center of the Earth is r. So you can work that out, and it turns out to be very small. And what NASA was trying to do was detect the gravitomagnetic field of the Earth, and also that because the mass of the Earth's there, Einstein said it would warp Earth, and the NASA experiment wanted to detect the warp of Earth. And I forget when they sent the experiment up, but 2004, I think. It's not written on there, but it might be written here. Let me just check quickly. No, I can't see it. 2004, I think. So if you look carefully, you can see the Earth, gravitomagnetic field, that little tiny white circle with a red K underneath it is the spinning ball. It's got an axis, angular velocity axis, which is looking at a star. It goes round that dotted circle. As the Earth spins, that dotted circle does not move. In space, it's fixed. If it wasn't fixed, if that ball went round with the Earth, there'd be no magnetic field. That's relativity for you. So you need it to move. And you can see when we look in 2007, having done, it took 18 months to collect the data. So 2004, 18 months. It took another year and so to detect the space-time curvature, but they've detected it. The next thing they wanted to do was to detect the gravitomagnetic field. And you can see how small it is, 0.042 of a second of arc. And they managed to detect that in 2011. Now, as my technical director once said to me, what's the use of gravitomagnetism? It's too small, forget it. Well, looking at that, that seems to confirm it. We're not going to be able to create a gravity field from that. Anyway, we'll go on about in a minute. Look at the bottom right-hand corner. There's the Earth spinning, and there's Australia, and at the very edge is New Zealand. And the people from University of Lancashire, Robin Tucker, and a few others at the University of Canterbury, they've got the world's largest ring laser gyro. It's fixed to the Earth, so it can pick up the Earth's angular velocity shown as omega E there. That's easy. They can do more than that. That omega E is like a spinning top. It precesses. I forget how big it is. It's about a meter or so. They can detect that oscillation of the Earth. The Earth's like a spinning top, no problems. What Robin Tucker wanted to do is a spinning top, so it must have a gravitomagnetic field. Hang on a minute. It's not moving relative to the Earth. What the Earth is doing, it's spinning relative to space. So now we're looking at the other way around. As the Earth spins, it's spinning relative to the sped into space. So what they're trying to do is pick up the gravitomagnetic field of space. It will be the same as the gravitomagnetic field that the NASA experiment will try to detect. Next slide, please. Right. Now, this is a conundrum to me. When you drop a mass, we know it's weightless. If you're in a lift and it drops away from your feet, it accelerates downwards and you float. But if you look at that equation there, if you remember the GEM equation right at the beginning, it said if you could change the gravitomagnetic field, you create a gravity field. And it's that gravity field that we are interested in. But we had that permeability term, that what I call eta there. Now, I've also told you there's an equivalence between gravity and acceleration. But if you're going to cancel a gravity field, you can only cancel it with a gravity field, not an acceleration. You've got to have a gravity field cancelling a gravity field. So where's the gravity field? We look at that and we say, well, that eta there, sorry, that's my thing. I don't know whether you can see that. Has that appeared on your pictures? No. Right. Oh dear, what did you, right, it's gone. So I can write that out as the gravitomagnetic permeability in space outside the mass and the gravitomagnetic permeability inside the mass. Now, outside the mass is 10 to the minus 26. We can forget it. So that first term on the right-hand side is negligible. So although there might be a gravitomagnetic field outside, we can't detect it. For the whole mass of the Earth spinning, you know it was tiny. But what's going on inside the mass? It's got a gravitomagnetic field inside the mass too. Is the gravitomagnetic permeability bigger? How on earth do we measure it and decide? Because if we could make it big, we might be able to control gravitomagnetism, and if we can change it, we've got gravity. Next slide, please. Well, I don't know what the answer is. The thing about a falling mass is unstable. It's very difficult to model mathematically. The thing I know that I can do, because I can base it on an analog, I know about line charges, so I can do a mass charge and I can drop it. And now it's steady because I've shown the big mass at the top there, but that's really that element in the middle of that line mass. And if it moves with a constant speed, I can work out all the values for the gravitomagnetic fields, both inside the mass and outside. And if you look about halfway down, I've written hx equals 1 over 2 pi r, and it circles round. And I've written h int, which is internal, and that circles round. And if you go and look in your electro-magnetism's book, you'll find what are called Biot-Savart laws, and they're exactly the same. Now, from our model of gravitomagnetism, we get eta, and that tells you that outside it's zero or virtually zero. Well, that's because the permeability, the density of free space acts almost like a solid. You might ask yourself, well, I can't see it. This is a question that people like Newton have asked, people like Maxwell have asked, and even people like Michelson. Why can't we see it? It's got infinite energy. We can't see it. Anyway, so if rho is infinite, that means the gravitomagnetic permeability is infinite. Sorry, is zero, because 1 over infinity is zero. And that is 10 to the minus 26 in real terms. And then if we look to see what the inside permeability is, we work it out, and we can work out what inside is going on. The induced permeability is V over R. Well, that's quite big. We should be able to measure that somehow. Even on a cylinder wall, it's the speed of it dropping over the radius of the mass. But how can we measure it? It's omega. Now we know we can measure omega in terms of rotation. So we know when we are doing gravitomagnetic tests, we always know what happens because we can do the equivalent thing. A rotation tells you what's going to happen. So we know what's going to happen with gravitomagnetism, except it will be a heck of a lot smaller. Next slide, please. Right, I said I would mention Faraday rotation. So the picture on the left with that yellow solenoid, and I've got a glass tube, and I've got a green laser passing through a polarizer, making the laser vertically polarized, passes through a glass tube, and it comes out the other side through another polarizer. If I turn the solenoid on and create a magnetic field, it makes that linearly polarized light twist. So if you now look on the picture on the right, that is part of a conductor, a line. I'm going to pass a current I through it. And you know, as well as I do, create a magnetic field around it. This was first done back in 1820 by Mr. Ørsted. Right, so how can we detect that field? Well, you can use, now I've got to use something that's in line with that magnetic field, and I can use Faraday rotation. If I put, instead of having a line chart, that was a linear one on the left. Now I want to do it circular. And if I create a coil and wrap it round that thing and pass a polarized light in and then pass a current through it, it's in line with the magnetic field, so the line will rotate. Right, believe it or not, this is what was done at BAE. This was based on a Boeing, is Gary in the audience? This was based on a Boeing idea, and it works. So they used it in lightning trials. They would have a structure and they would pulse it with a very high electric charge, and they would use that fiber optic coil, work out what the magnetic field was, and from that, using those Biot-Savart equations, they could work out what the magnetic field was. Right, so now the question is, can we use the same idea to detect, that was detecting rotation of a magnetic field. Can we detect rotation of a gravitomagnetic field in the same way? Well, magnetic fields and H fields are twinned anyway. We've already accepted that because charge E, when it moves along with mass E, so the two work together. Can we use mu metal to separate them? Don't know. Does Faraday rotation occur with gravitomagnetism? I think it must do, but is it big enough to detect? In fact, it makes me wonder whether the fact that whether Faraday rotation occurs at all might be because it's mixed up with Faraday rotation, with gravitomagnetism. And if you took the gravitomagnetism away, I wonder whether magnetic field will still cause rotation. I don't know. Next slide, please. I'm very keen, as you saw right with my early meeting with the universities back in 1990, Faraday's first gravity experiment. I was just looking in a book here, which is about Faraday. And at the end, it's about the Zeeman effect, which you may or may not know about. Zeeman was looking for the change in light when you put a magnetic field. So Faraday had a spectrometer, was shining light through it and getting all the various patterns, and then putting a magnetic field in it to see whether it changed. It didn't do anything. That was in about 1860 something. And Zeeman was looking through Faraday's diary and wondering, Faraday tried it. I wonder whether there's anything in it. He tried it, and guess what? With more sensitive equipment, he detected it. Well, there you are. So Faraday's mind was just amazing. He wasn't a mathematician, but he was brilliant at understanding what nature did. So this is Faraday's first gravity experiment. If you think of his induction experiment, it was very similar. What he did was put a coil round an object, a cylinder of something, iron, copper, or bismuth. He then attached a coil around it and he dropped it because he thought, as that mass dropped, he thought that it's just possible it might create an electric current, and he would see that on the gyro. Just like his induction experiment, he thought it would only be temporary, so you have to be very careful to watch it. And his first experiment, it did do that. He thought he'd found something, but then he realized when he dropped a wire through a magnetic field, it created an effect, so he had to twist the wire. And when he did that, it didn't do anything. He spent some time doing other experiments. He never went back to this one. And I've looked at it and I've thought, I think he was probably right. Something does occur around it. Well, theoretically, it does seem to be the graviton-magnetic field. But how are we going to detect it? It's no good looking outside that mass. We've got to look inside. Now, inside, of course, is a bit difficult, but we can actually put the coil on the surface. The thing about gravity and gravitomagnetism, in the NASA Gravity Probe B experiment, they had to, that ball that was spinning, they had to enclose it in mu metal. They didn't want Earth's magnetic field interfering with gravitomagnetism. Gravitomagnetism is not shielded. Gravity is not shielded. We've only got one sort of mass, so you can't shield mass from outside effects, nor can you with gravitomagnetism. So if you put that fiber optic coil on the surface of the falling mass, what's going on inside the mass will create a gravitomagnetic field. You can't shield it, so it will get to the surface and it will be on the surface. It won't be outside the surface because that's where the permeability is so small, but it might still be there on the surface. So that's my idea for checking it. Of course, you don't really need the mass itself because the fiber optic itself has got mass. You could just drop a big coil and see whether there's any effect on polarization. So those are the two ideas. Is that the last slide? Oh no, next slide, please. So I think I'll read it very quickly. Have we got time? No, I won't read it. What I'm saying here is that Hans Ørsted discovered the magnetic field around a moving charge in 1820. We want to detect a gravitomagnetic field around a moving mass. If we can do that and start probing it in a laboratory, just like everybody else probed what Ørsted had discovered, we are going to be able to probe gravitomagnetism and work out how to change it. Once we can change it, we can change gravity and make gravity. That's the end. Thank you for listening. Okay, Tim.
Okay, wonderful, wonderful. Thank you, Ron. And I should apologize for some of the difficulties. There's a lot to manage having Zoom going at the same time as screen share. It kind of shifts the controls and stuff around. Thank you very much for presenting. So I'd like to do Q&A session. Let's jump right into that. And I have to go in here and chat and take a look. Now, normally I manage this as we go, but again, with screen share, it kind of hides it. So let me see. Or does anyone, let me go to gallery view here. Would anyone just like to raise their hand? Let me see, we have Gary. Okay,
no, I'm waiting to Rob James.
Oh, well, let me go to Gary first because he's on my top left here. Gary, what can I help you with?
Yeah, wow. Thanks so much, Ron, for this really fascinating history. I'm wondering, was there ever a systematic attempt to look at unexplained aerial phenomena, their behavior, and did that guide any of the work of Project Greenglow?
Podketov, did you say? Sorry, Gary, I didn't get the end bit.
Yeah, I was more interested in unexplained aerial phenomena. Did you ever have a systematic look at that as part of Project Greenglow? And if so, did it guide any of your?
You mean the kid inertial thrust machine?
Well, as an example.
We never went back to it.
Okay.
Never.
Okay. So let me go to Wayne now. If he's with us, Wayne, are you have your hand raised?
Yeah, I'm here.
Okay.
Yeah. Yeah. Hi. Very fascinating talk there. I'm just gonna turn this. Sorry. I have a silly background on there. It's kind of embarrassing from a different call. Anyway, the graviton-magnetism thing, I've experimented quite a bit with rotating like brass cylinders and stuff, looking for graviton-magnetism, thinking that it might be happening on the nuclear level, like the rotation of the nucleus or the angular momentum of the nucleus that would have its own graviton-magnetic field, and then perhaps by rotation of a large mass, a metal disk, that polarization might happen, making it more detectable. But I just don't know. I don't know if there's a way to mathematically calculate what that field would be. And I guess that's kind of my question: is that knowable or calculable, so we can make some kind of prediction and know what sort of range or ballpark to be looking at with instrumentation. Thanks.
Do you want me to say anything, Tim?
Oh yeah, yeah. I would say go ahead. Go ahead.
I've actually done a calculation of that, Wayne, in the book, plugging the book, which you can't buy now, but you can get the electronic version. But in there, I did do a calculation. There's two things. One, I'm just trying to think of the man's name. There was somebody back in the 70s. I remember Lathwaite showing me his papers, looking at the atomic. I wish I could. Perhaps Rob Chambers can remember his name. I can't remember. There was also another paper, which I've got, but I can't remember his name, where I think it was an AIAA paper. No, it was an IEEE paper, where he was spinning two cylinders very close together. Again, it's in the book. I could look it if I've got time. But so the answer is, at the moment, it seems to be too small. That's that eta parameter, 10 to the minus 26 across space. Now, the Russians, way back in some of their papers, they were also looking at that effect. I've never found any more, but it was mentioned in one of Robert Forward's papers.
Wonderful. And Rob, did you want to add anything to here? Let me ask you to unmute there.
Well, I can add a little bit of color, maybe. A couple of things that Ron mentioned, which might be of interest. When he mentioned HOTOL, which was one of the projects that was worked on in the 80s and so on, that has essentially now become, well, people who worked on it have become part of Skylon, which is potentially a better way to get into orbit, a more practical way to a single stage to orbit vehicle. So that kind of that, so there are still some activities, but again, it's quite small scale. Also, the radar question during the war, one of the earliest examples I think was the Mosquito, which was a British fighter bomber, which was wood, and I think this is when they realized that they couldn't detect them. So this gave a clue as to the early stealth capability. So yeah, and yeah, so just to add a bit of detail to some things that Ron mentioned.
Oh, wonderful, wonderful. Well, and again, I know you have a presentation as well, although the way it's looking, we'll
Yeah.
probably, if you're open to it, maybe next week. So
Yeah, yes, no problem at all. Yeah.
absolutely.
Yeah.
So does anyone else have any questions?
Who's going to do the experiment for me? I want to know.
Yes, I'm trying to figure out how to use the raise hand icon thing, but I've got my hand raised on camera. I have no idea how to put that little icon thing that Wayne popped up there. So Wayne had played around quite a bit, as he talked about, with graviton-magnetism, and it's something that we were looking into in our little research group. We have a WhatsApp sort of think tank about alternative propulsion and gravity control. And so one of the experiments that was proposed was, is there possibly a coupling between a magnetic field or a moving magnetic flux and the trajectory of a laser beam? Because laser beam is effectively controlled in terms of its divergence or its curl. It can be modified by the curl vector theoretically, because a laser beam has a magnetic and electric component. And so if you already partially saturate the magnetic component in space, it may be possible, but it's one of those strange things on the edge of physics where it's not really looked at about a lot. Physicists don't really want to talk about it. In academia, it's so unstandard that you can't really get many people to look into it. So what we did is Wayne performed an experiment with a small low resolution diode laser and put a large magnet, kind of like this one, large neodymium disc magnet next to that beam, and he crossed the beam across in this direction, and by basically waving this magnet up and down, bouncing it across the room at that point, and then having it reflect back onto the wall, so a total distance of about 30 feet, he was able to notice a tiny little change in the total position of the laser beam. Now, there's a lot of reasons that it could have happened, but I wanted to do the experiment myself to see if there was anything to it. So we performed it again with a laboratory grade helium neon laser, which has much better beam profiling characteristics, and we bounced it a total distance of about 40 feet and looked at our beam profile on the wall. And we were able to get that beam to wiggle back and forth consistently about 0.5 millimeter. And so we noticed that if we move the cylinder magnet up and down like this, the beam would move in and out. And if we move the cylinder magnet, back and forth like this, the beam would move right or up and down. So it seemed like the beam almost pushed itself away. Now, it could be magnetohydrodynamics, we thought. Maybe we're affecting the air and we're causing lensing because we're grabbing onto some free charges in the air and maybe, refracting it. But with the idea that you can use a magnetic field to curve a laser beam, this Faraday effect system, then it kind of offers the possibility that maybe there is an interaction with the trajectory of a laser in a divergent magnetic field, that maybe we could actually bend that. And it would lead to the question of, if we're not actually bending the beam itself, are we modifying some space-time coefficient that causes the beam to take a slightly different path, even though very, very small? Any thoughts on that would be really wonderful, because we're going to continue this experiment, and what we want to do next is get a mirrorless camera and take the CCD and use it as a detection mechanism to show and record very tiny changes in the position of the beam, and use an electromagnet so we don't have any interaction there, and we can effectively just show that if the beam's not touching the magnetic poles already, it's obviously not some kind of diffraction across the surface or reflection. That way we can eliminate out the variables and show that we really can affect the trajectory in a vacuum. So yeah, thoughts, if anybody has any. I guess we're going to keep on doing the experiments then, and we'll let you guys know. It's a weird thing, eh?
Well, thank you, Jeremiah. So let me go back to Ron. Let me mute you out, and then I'll mute. Let me see. I'll mute Paul. We'll just get it back to just Ron. Let me read a couple of comments here. One thing, Gary just mentioned this. I'm going through the comments. He said a UAP sighting with a witness wearing polarized sunglasses saw dark rings around an object, which may indicate Faraday rotation. Gary, do you want to ask?
Yeah, I guess if I had to frame it as a question, it would be, could this Faraday rotation be a result of gravitomagnetic effect versus what they thought at first, just a strong magnetic field? Have you looked at that, Ron, using picking up Faraday rings or a Faraday rotation effect in the polarization of light to measure gravitomagnetic fields?
I haven't. But I know there has been work done from starlight and things like that.
Thank you.
Yeah, so you're on the right lines.
Okay, wonderful. And then, so Eric Hermanson had said, and again, I should apologize. I've got folks kind of coming in and out of the room as we speak, so lots of distractions. Eric Hermanson had talked about time dilation in the region, not a magnetic field. Eric, is that something you wanted to ask about?
Yes, I don't know that I'd really want to ask about it. I'm just suggesting that a different mechanism is at play.
Oh, okay. Okay. Sorry. I just wasn't sure. I'm trying to go through all the comments because I have a backlog. So
I just wanted to say thanks, Eric, for that. Yeah, we don't know what it is, and I don't really have a personal opinion about what it is. I'm just trying to figure out maybe what's going on and eliminate what it's not, and that would make sense. I didn't realize that you could affect just one parameter like that and still change the trajectory of a beam. But there's, I still have a lot more to learn yet, so I'm learning as I go here. Thank you very much for the info. I'll look into that.
I hope you're going to do the experiment.
Oh, absolutely. It's all down to the experiment. I mean, at the end of the day, I'm an engineer, not a physicist, and not a professor. So I'm definitely all about doing the experiments and seeing what happens, and then sharing those results.
I wish I was. Yeah.
And I'm just trying to understand before I talk about what it is that we're looking at. What's that there?
My cylinder and my piece of glass, and I've tried, but it needs. Well, it really needs someone good at experiments, and I can see that you are.
Well, thank you. We can't wait to share our results with you guys. We'll be doing that experiment over the course of the next month, and we'll have better measurement systems than we've ever had set up, so we can give true differentiation patterns and demonstrate what's going on. Nice.
Well, gentlemen, let me jump in real quick. So I think that we're all caught up on questions, and we have about half an hour until Nick Pope arrives. Do you want to just kind of go to an open, or actually there's Paul. So after there's Paul and Wayne. So the minute I mention it, questions pop up. I was going to say, do you want to go to an open discussion? But let me go to Paul.
Let me ask two questions. When you talked about a lot of programmatic issues, when Huttel was coming around, was that taking away some of your funding?
Sorry, Paula. I do know you, but I couldn't quite hear the question.
When you were talking about programmatic issues,
Right.
when Huttel was around,
Who?
Hotel or Huttel was around,
okay.
did it suck up your funding?
No.
So it's two parallel programs then.
The Greenglow program was tiny, absolutely tiny. I don't know whether I should tell you on the thing. I mean, I started it really in 1986. It was finished in 2004. I doubt whether we spent £100,000.
Jeez.
Yes, well, that's the UK for you. The NASA program cost, the NASA GPB program cost $750 million.
Hey, I don't get any of that.
No, maybe not. But,
the next question I have is can you give us some heads up about what inputs you got from Graham Innes?
From?
Graham Innes.
Oh, Graham Innes. Not a lot.
Okay.
What happened was, have you heard of the Royal Aeronautical Society in the UK?
Yeah.
We have what's called the Royal Aeronautical. I got a call from him for me to meet him there in London, and I went down. That was my first time I'd met him, and he's certainly very talkative, and he knew a heck of a lot about what was on the web in this subject area. But I thought he was a UFO man. And the one thing I had to be careful of was not going back to where I worked at BAE and said I was working on UFOs. I'd have been sacked. For some reason or other, people are scared of UFOs.
Did you happen to look at Potter's design? Paul Potter's design?
Potter's design?
Paul Potter's design.
I don't know.
Okay, It's a copy of what Andreessen did about a UFO.
Right. I don't know it.
Okay, I was just curious.
Right. No, I don't know anything about it.
Thank you.
Okay, so let me go back to Wayne. Wayne.
Yeah, just two things. One I wanted to add regarding the laser deflection experiment was that I noticed a similar slight deflection in a beam when I put near it a rotating cylinder of bismuth powder in epoxy, and it seemed like that had some effect on the beam as well. But I need to do more experiments with that just to verify it. And second thing was I was hoping Eric could elaborate more on the time dilation concept and what that actually means in terms of space and deflecting the laser beam. Thanks.
Yes, I just sent the group message. You know, it's not something that I can elaborate on in a short amount of time in a way that would do it justice, in that it's, you know, an assembly of my understandings from quite a few years now of looking into this and thinking about it. And so if you send me your email address, I will you know, send you some of my ideas, and you know, we can discuss it offline. And if Tim wants to talk to me about doing my own presentation, I'll certainly think about doing that.
Sure, absolutely. Yeah, let's talk about that, Eric, for, you know, hopefully maybe the 30th or the next after that. Now, we also have some comments from Michael Richardson. Michael is having some trouble with his audio, and that's not something I can really assist him with right now. So, but he's saying that gravity is an entanglement, not a force. Time dilation is possible when time flows faster on one side of a photon. And again, these are things, you know, hopefully we can have him back in the future to talk more about this, but he does have some comments in chat there, as well as Eric's, and we definitely want to follow up on that more. We should also welcome Nick Pope. I just saw him come in. And so do you guys want to do a few minutes do you want to take a kind of a short open session, or how should we do this?
Has Wayne seen that book, Tim?
Let me see, the Time Traveler by Ronald Mallet and Bruce Henderson.
Yeah.
Wonderful. Okay, and well, guys, why don't we do this then? Why don't let me see, I will pause recording, and why don't we take a short break?
1 second. I had a question.
Oh, okay.
Can you expand a little bit on the gravitomagnetic field? I saw you showed a picture of the Earth. Is this some sort of connection with the spin of the Earth, or are we talking about the gravitic field of the Earth, or the magnetic field of the Earth? What exactly are we, you know, working with there?
Is that over to me, Tim?
Yes.
Yeah.
Okay. Well, the Earth has got a magnetic field, and it's also got mass. So it's got a gravitomagnetic field. So the two go together. Now, if you're going to detect,
with respect to the sun's frame.
right, if you're going to try,
Different frames of reference. There's the sun is spinning as well, and it has its plane, and then Earth has its plane of spin. And something that I found very interesting when I was looking at the gyroscopes with Tom Vallone and Mike Gamble is that they noticed that the best results were found when the gyroscopes were offset by 23 degrees, which is the offset of the Earth's axis. So I was wondering if there's a connection there, and if you can elaborate more on that.
I think if they are connected, there will be an effect That's all I can say. If they are connected. If they're not connected, then you've got that permeability factor, 10 to the minus 26. So you can forget it. There's no effect. Don't forget that graviton-magnetism is equivalent to angular velocity. But whereas graviton-magnetism field can be experienced across space, you don't get any effect from angular velocity. The angular velocity of the Earth has no effect on anything except the gyro, of course, because you're fixed to the Earth. So it will affect the gyro. The gyro will be fixed in space, but because you're fixed to it, it will look to you like the gyro's moving. There is also a gravitomagnetic field there. It's too small to detect. The Russians had an experiment, or at the same time as NASA Gravity Probe B was starting, they wanted to do an experiment on Earth to try to detect the gravitomagnetic field. But you've got to be careful that relativity always comes in. If there's no relative movement, you won't see anything.
Right.
Can I jump in? Can I jump in with the angular velocity? With one thing on the angular velocity, if you think about a satellite in motion in a stable orbit, it has to travel an exact velocity, angular velocity, in order to stay in orbit without being pulled down to the Earth by the Earth's gravitational field. But really, it's the gravitational time dilation, magnitude of time dilation at the satellite volume that's pulling it down toward the Earth. And so it's moving at a velocity tangent to the Earth at an angular velocity that creates a time dilation, a clock rate change that balances out the clock rate change that's imposed on it by the Earth's gravitational time dilation. And they equal each other. And I think that's where the time dilation comes into play. Thank you.
Is that Schuler? What's called Schuler something or other?
Also, one other thing I wanted to mention, we are working with gyroscopes, and we are also trying out Podklanov, both those experiments that you mentioned. So if you stick around in a couple hours, we're going to be showing our replications of it. I've already gone through several prototypes of the gyroscopic device, and I have it all on these little remote control, like RC remote control setup. So you can try any iteration you want with the control of your fingers. And it all comes down to programming at this point. What angles do we want? What movements? The first prototype, we had some mechanical difficulties because the gyros I got, the servos that I got were completely inadequate and the whole thing started falling apart after about a minute, and I was afraid the gyros would fall. By the way, the gyroscopes, the best gyroscopes are made in England. Sure you're familiar with that. You get them at gyroscope.com. They're expensive, but they're worth every penny. Precisely balanced, and we have a setup with 4 gyroscopes because Mike Gomble is just trying 2, and he noticed that it was a sort of a pulsing effect. So I was thinking, if you're having a pulsing effect and you're not able to get it, permanently linear, maybe you should have 4 gyroscopes. This way you can clean up your AC, your alternating pulse. And I think that's precisely what we're seeing. We just need to get the software figured out of, software being how to wiggle our fingers while we're trying this device. And it's actually right here beside me. Another experiment that we're working on is a spinning disc inside of a magnetic field, and there's reason to believe that might create some sort of gravity shielding effect. Although my power supply is having a little issue, I might just use a battery for it for the experiment later on today, just to pulse it with enough energy in order to get like some decent field, because all we were dealing with was around 90 Gauss, which is, not even a weak magnet puts out more than that. So there's a lot of experiments coming on. I think it's around 2 hours from now when we go live from the lab.
Yeah, and that'll be really exciting.
Yeah, so I've got one more question for
going back
directed
to
at Ronald. in that slide where you show the Earth's precession and its magnetic field, and they're trying to measure the difference between the gravitomagnetic field perhaps of the Earth and the gravitomagnetic field of space itself. You mentioned that they're trying to use this reference frame in space to detect the precession of the Earth, although it's very small and we're looking for these tiny numbers. So I guess my question would be this: is the Earth's rotational axes of alignment and its position with the sun perhaps tied to some other external larger gravitic field that's coming from somewhere externally in space or from space itself at our local place in space? I'm just basically what I'm asking is why does Earth have its specific alignment, and why does it have its specific orientation and rotation around the sun, and why does that have its orientation to the rest of the galaxy? Is there some other larger galactic level field going on that that our little solar system is coupled to?
I don't know. God.
Sorry, didn't mean to ask a really far out there question, but I wonder if it's related though.
Could be. I don't know.
Sorry. Thank you though.
Okay.
If you talk about off the wall questions, I have a question. Does anybody have any information at all about the magnetic field about a UFO? We may have some measurements in terms of the electric field based upon a radio going off the air, but is there any magnetic field data on this subject?
Paul, the link I sent earlier in the chat box, which I can send again if you want, was the 1953 Yuma, Arizona sighting. And that was a famous sighting because a scientist made the sighting. His name was Wells Allen Webb, and he was wearing polarized sunglasses. And in his polarized sunglasses, he saw dark concentric rings around the object, meaning that there was, his take of it at the time was, it must have been an extraordinarily strong magnetic field around the craft to cause a significant enough polarization shift around the craft that the polarization rotation would cause so many concentric rings. I think he counted almost half a dozen concentric rings, which would be an impossibly strong magnetic field. But when I saw Ron's—
Okay, now these are on the outside.
On the outside of the craft.
This is on the outside of the vehicle.
Circulating around the sighting. But when I saw Ron Evans' presentation— Go ahead.
I'd love to see the paper.
Yeah.
If you can send me the paper, I appreciate it.
Actually, let me put it back in the chat window right now because I was with us too, and Nick has probably seen vastly more UFO and UAP sighting data than any of us have. But this was collected by—
Let me ask you another question, Gary. Gary, let me ask you another question. The implication is that the glow in these rings are magnetic.
Well,
how would you say they weren't electrical?
Magnetically caused.
What if they were electrical?
Well, when I saw Ron Evans' paper, he was suggesting that Faraday rotation may also be a way to detect gravitomagnetic impact, which I had not thought of until I saw Ron's paper just now. And so it may very well have been these rings that he was attributing to a strong magnetic field may have been caused by a gravitomagnetic field generated by the craft. So it's an alternate explanation for these Faraday rings that I had not thought of before. So I thought that was an interesting angle that Ron brought up, that a Faraday rotation may be another way to detect gravitomagnetic fields.
So when I get a picture of a UFO and it's a bright glow, what you're telling me is that I should be able to get some information about the magnetic field.
Yes, you should be able to, if you have polarization detection, in other words, if you have two detectors pointed at it, one with the polarization oriented this way, the other with the polarization oriented the other way, 90 degrees, that if you compare those two and you look at the phase, you look at the polarization, if the polarization is shifting across the X or Y axis, that polarization shift may be from Faraday rotation, and that Faraday rotation may be able to tell you something about magnetic field strength.
But I don't get anything out of, let's say I have a picture that has an IR and an UV picture. Do I get any effects over there?
No, the problem is it's not. Yeah, you're not looking at it, not unless the data is polarized.
Okay.
You have two infrared detectors that are polarized in different ways. You can see it. The reason this scientist was able to see these rings at all was because his sunglasses were polarized. Otherwise, just a regular photo, you're not going to be able to see anything.
Well, Gary, that information is really very useful. And for Nick Pope, this is the type of stuff we're talking about. Little tidbits of information, that happen by chance that nobody would think about as important. But Gary just brought this up, and this is going to be very helpful. We should probably reach out to Stephen Greer and all those people who try to make contact with flying saucers all the time and ask them to try this experiment as well. Because like they get a close up and they can get some pictures of that. That will be very useful in the lab.
Certainly, if they had a polarization filter, that would be a fantastic tool to see these rings.
Those are.
Let me jump in really quick also. So we have some chats here. Mark Fiorentino, I'm not sure if Mark would want to jump in or not, but he did in chat, he said the Air Force used to bring magnetometers to UFO landing sites during Blue Book. Actually, I've heard that before as well, magnetometers being something people have tried to investigate those with. And then Sean Richter had talked about access to a Google Drive database. And he had said, email him at extraterrestrial.engineering@gmail.com. And Sean, maybe you could clarify what is in the database that people would email you for. But again, for YouTube listeners,
Well, Tim, let me ask you a question. Let me mention something.
Sure.
Okay, I might see it on the footprint after it's gone, but I'm more concerned about what it is on the vehicle itself in terms of its propulsion. Now, Bruce Cornett is on your list over here. He's taken lots of pictures. I'm just curious if Bruce has looked at anything with a polarized camera lens.
Bruce Cornett, right?
Yeah.
Let me ask him to unmute. Sir?
It looks frozen.
Oh. Yeah, he might be. Yeah, he might be frozen.
Okay.
Okay, there we go. Hi, Paul.
How you doing?
Yeah, I just put something in chat on this. The data that I have is published in my 2019 book called Unconventional Aerial Phenomena in the Hudson and Walker River Valley of New York. You can get that on Amazon or on Kindle. What's important in those data is that I recorded all sorts of electromagnetic field effects on my time exposures that are quite interesting. The electromagnetic field rotates clockwise, counterclockwise, clockwise, counterclockwise as the craft is moving along. And take a look at this. There's a lot of important information in there that could help determine what works and what doesn't.
Do you mean to say that the entire field of the craft rotates clockwise and counterclockwise as if it's reversing, or do you mean that it has two simultaneous fields that are juxtaposed to each other happening?
I record the movement in the lights. These craft typically had navigation lights, headlights, and things like this, and these lights literally rotated and in one direction and then immediately in the opposite direction, back and forth and back and forth.
If I may ask, what was
while the craft did not rotate.
What's the time cycle at the speed that these things reverse?
Slow by comparison, because you can actually see, on my time exposures, determine the length of time and the number of loops. Might have had 2 or 3 dozen of these loops within a 20-second time exposure.
But Bruce, your ground observation site is fixed, right? So if you're seeing the variations of the field, it's at that fixed location, true?
What you're talking about, the Pine Bush location?
I'm talking about your measurement, your electromagnetic measurement. The craft is moving, but your measuring site is fixed, right? So you're picking up as the craft is moving variation in that location, true?
Correct. If you can hopefully hear me without my voice breaking up. I was followed home one evening from work by a Boeing 707 that had no insignias on it. It was totally black, no external engines, no windows. It crossed in front of me on the New York Thruway and then proceeded to cross the highway as I went home to Middletown, New York. When I got home, it was the sun had already set. I ran in, got my camera, set it up, and it came back and flew over me. It was what appeared to be a full size.
Bruce, you're breaking up pretty badly. Yeah, Bruce, you're breaking up pretty badly. I think we've
Wingspan of a Boeing 707.
Oh, okay. Okay, well, let's hold for now. I'm going to mute everybody back out. Guys, so one thing I would just like to say, let me see, we should all put our hands together and do a giant thank you for Ron. Mr. Evans, thank you so much for presenting. I wanted to get that out of the way because we were pushing right up against Nick Pope's time slot. But Ron, thank you again. That was a wonderful presentation, incredibly in depth, and thank you very much.
Tim, did you get the last part? I was cut off.
No, and so if you want to give it another try, if you could try to squeeze it in, we've got in just a minute here.
Okay. The images that I captured using the chopper device showed how fast the craft was, the Boeing 707 was moving, and it literally stopped and backed up. And I have that on film. All of that is on the internet. So
Oh, okay. Well, Bruce, you're breaking up again, so let me mute you back out. Okay. Oops. Yeah, it looks like Bruce is actually looks like he's frozen. Okay. So Ron, thank you again. Let me mute you and I will go back to, let me see. Now let's go to Nick Pope, who is joining us. We've got about 2 minutes here.